This is the last video of this three-part video on practical PID controls. The first one was on what is the PID controller. Second one, how do we tune a PID controller? And now the third one is on practical modifications we're going to do. So first of all, remember our control law of a PID controller was K times E plus 1 over Ti integral E of t dt plus Td dE over dt. So now this is where most control courses stop, and then we move on to finding either control strategies or we're doing something else. The problem is that this is only sort of the tip of the iceberg, and more importantly, it's not going to work. That algorithm here is not going to work in practice, and I will tell you why. And it has to it's related to each and every part, P, I, and D. Okay, so let's start. Consider a step change. Okay, so I have the step change here. I have now in pink my set point that changes stepwise, and if my controller is a PID controller, it's going to follow the status step change. Okay, so this is my Y. Right. So if I can draw this differently, and I can draw the control error. E is simply R minus Y. So if I subtract that, if I subtract R minus Y, I will be at 0 up to the step change. And then my control error will suddenly become large, and it's going to be this large. And then after that, it's going to decrease, going to smaller, and it's going to decrease like that. Not exactly, but sort of. Yeah. So think about it. This is the error in between. It's always this height here. So this is the function I wanted to draw down here as well. Okay, so what's wrong with that? Well, the problem is, what happens to the derivative dE over dt? What happens to that? Over time. So the derivative of 0, of the error of 0, is 0. But what happens at time t equals to 0 when I apply the step change? It's going to jump. So it's not only going to jump a little bit, it's going to jump sudden, and it's going to be, that means the derivative will become an impulse. It will become very big for a very short period of time, because the derivative here is, in this picture here, is a straight line going up. And so the slope of this increase is infinite. So I have for a very short time, I have an infinite slope. And after that, well, it's like this here. It goes negative. I have a negative slope, which goes down, and it's going to go up again. Okay. So you can see that this bit here is very bad. This is what we call a derivative kick. This derivative kick will destroy your actuator in one go. It was going to give a big jump, a big signal onto your actuator, and your actuator, your valve or your motor is going to go poof. So don't do that. And this is why we don't implement it like that. So what we do instead is we implement, well, first of all, we see dE over dt is equal to dR over dt minus dy over dt. And dr is this curve here. So if I do the derivative kick comes because of the r. So for us with a constant set point, we have r equals to 0. So the derivative, or r is constant, so the derivative of r is 0. Derivative of constant is 0. And it's 0 here, but in between it does this crazy kick. So don't use r. Okay? So what we're going to do instead is we are replacing instead of using the derivative of dE over dt, we only use the derivative of this bit, because this one here is 0 most of the time in any event, and then for some crazy time it goes poof and destroys the actuator. So instead of using dE over td, we use minus td dy over dt. So that's the first quick fix. Now we have to implement it like that. If we don't, we'll blow our actuator in one fell swoop. Now, we have a similar problem with the proportion part. P part has a similar problem. Not as big, but still. Can you see that? So the proportion part is proportional to the error. If we change the, if we apply a step change, the actuator will get a signal that's suddenly very large and then drops. So at least it doesn't spike, but at least, at minimum, it's going to give it a bit of a kick. Yeah? So a little bit of a bump, of a step, and that's not very good either. So this is also not good for the actuator. So this step here, so the P part is a problem, no impulse, but at least we have a step. That is not good. We've got the sudden increase. That's not good. So the solution are set point weights. So we call this a set point weighting. And we put a weight onto the set point, and so that our control law looks like that. U equals to K times. Instead of E, we're using a factor B times R minus Y. So we're replacing E, which stood for R minus Y, with B times R minus Y, and then we have the rest as follows. Plus, good exercise to draw this again, integral E of t dt minus td dy over dt. Quick fix. So we call B as the set point weight. If B equals to 1, that means we effectively don't do any set point weighting. So no set point. Because then B equals to 1, we just have R minus Y, which is E. Okay, and this could be fine for some actuators, for some control loops. We have to decide. We have to see how sensitive it is, how big we are expecting the step changes to be. The alternative is that B is at some point between 0 and 1, and often the implementation only gives you the choice between 1 and 0. And here we have set point weighting. Ideally, we have something in between. And you can see, so if we choose this here, we react slower. But it will be smoother. So we act slower but smoother to set point changes. Okay. If you don't know about that, you're going to run into difficulty. Okay, so now we have adjusted our derivative part, our D part, and we've adjusted our P part. And what about our magical I part? That was so amazing. It fixed everything. There was a problem there. We have another problem with the I part. And this problem is called integral windup. So the name is in the pudding. What's the expression? It is evident from the name that it relates to the integral action. It's called, and this comes from the fact, it stems from the fact I wonder if I should call it fact. It stems from this common occurrence that the actuator is always limited. I'm writing limited, but it actually is always limited. We never have an infinite actuator. We always have a maximum output, control output signal we can act on our process, and we have a minimum one. Okay, so for example, a valve can be fully open or fully closed, but not more than or less than that. Okay. So let me explain what happens. And I have to be very diligent and do this very carefully. So I do have my, as I always draw these diagrams, I have my process variable and I have my controller output. Okay. So we draw in my pink, my lovely pink set point change. So this is going to be my set point. So I do a change in the set point, right? And imagine I am at a valve position that is already 80% open. I'm applying a rather big step change in my, so that means my my process variable is quite far away from my set point. So I have a process variable here as well. So pink is Y, this is green, and pink is my set point. Okay. And in blue I'm going to draw my my controller output U. All right. Okay. Here is the point where the problem, well, not where it starts. Okay, so and then I have here 100% open. Okay. So now I see there's a huge discrepancy between reference point and controller reference point and process variable. This is quite big, so I need quite a lot of control action, and it's going to increase my process, my controller output, meine Stellgröße, up to a certain point, up to the 100. What's going to happen to my process variable? It's going to increase for a while. Okay. But then, because this one here is limited, it's going to stop increasing. Right? It's only going to up to here. It's only coming up to this point. Right? So here is the point of departure. This point here. So what happens at this point, because of the integral action, is that the integral controller will start seeing this discrepancy over a period of time, and as a result it's going to integrate. That means, because it's sort of constant, it will increase in an integral way over time. So this is going to increase up to a point. So there's nothing wrong with this controller output. What can we do? We can't get any more. That is not the problem. The problem is that this control action, and this I should call U calculated, this keeps on increasing, and that is wrong. So I particularly see this. So I don't see this at this point. There's nothing I can do. Why I need to fix this. A problem comes if you see, oh, hang on, this was much too much, and I actually can't do this, and I don't need it. So what you're going to do is you're going to decrease your set point again. Now what is going to happen? From this point onwards, if you're using your calculated controller output, this one will have grown up to this level, and then okay, at this point, we see, hang on, there's a big discrepancy here between those two signals. So it's bigger than this one here. So it's going to increase my calculated controller output. It's going to be quicker than decrease than the increase, because the increase was only this bit and now I have this discrepancy. But still, my actuator is going to keep on getting stuck here. So that means I don't see any change in my process input up to this point here when I decrease. So what's going to happen if I carry on integrating is, here then it's going to go down, because here finally my controller output has come down from this really large value that is above 100%. And then things work again. So the problem here is this particular part here. This is the problem here. This takes too long to come back, and it happens because we had integral wind up, and the integral wind up bit is here, this part here. We can call this point here, this is where it builds up. This is called the integral wind up, which would have to be followed by an integral wind down. Now, so it's the integral wind up, wind up. So you think, oh, is this really so terrible? And the answer is yes, it's terrible, because think about like someone left it on for like a couple of days. Think how high this has gone up, it's shot up, and you will never get it down. If it's been high up, you will have to wait another 2 days for it to come down. You're thinking, oh, my controller is not working. So it is not optional to not deal with integral wind up. Fortunately, it's actually very simple. You just have to know about it, and this is the difficulty. Now that you've watched this video right up to this point, you know about this problem now of integral wind up, and you will make sure that your integral action part is reasonable and you can use it. What's the quick fix? The quickest fix is simply say, well, if u is greater than 100, that's one quick fix. Just set it to u equals to 100. Yeah. So we may have to make sure that this yellow curve doesn't happen. We'll be working with the blue curve. What you can also do is, if u is greater than 100, you deactivate. Or if u equals to 100%, you deactivate the I part. You say, well, I'm not doing an integral part. I stop that. Yeah, I'm only going to count the integral again once I get to this point. So that's another option. You can do both of them. You have to, obviously, this is also not only true if I'm at an upper limit. So I've drawn this here for the upper limit. It also obviously is also when you're at the bottom limit of your actuator, you will see exactly the same occurrence where you can't decrease more than 0%. It's your minimum flow rate. Okay. So these are three of very important modifications without which the PID controller will not work satisfactory, especially for the process industry. So we first worked around with the derivative part and said, well, don't have the derivative kick. And then we said, actually, we have the similar problem with the proportional part. So we introduce set point weighting. And lastly, even our lovely integral part, which is otherwise doing the world for us, has a problem which is called integral wind-up, which we have to deal with. We don't change those equations, but we're going to add some logic. This is if, then. Yeah, if u equals and then. So we have to implement a certain form of logic. What's next? We still have to see how the PID controller is actually implemented when you're moving on to discrete time and when you move into a computer program. Right now we have a differential equation here, but this is not how we're going to implement the PID controller. We're going to implement it in a discrete time format with difference equations, and this is what we're going to see next.